Okay, we are now going into the second chapter, which is much more straightforward. And I have recorded this material in some form for other courses already. You can see it in the Ocean Atmosphere Dynamics course I have on my channel and the Bending the Curve chapter as well, several podcasts. But this material is organized a little bit differently with a little bit more emphasis on terrestrial ecology. Plus, if you're going to read this book, then I want you to be comfortable with the material, so I will cover it as presented in this book and add a lot of stuff that I think is necessary for updating. Excuse me. Okay, so it's Fundamentals of Climate Change Science basically provides a high-level summary, so we won't get into too many details. We'll look at all the main points about the observations, processes, models of climate and terrestrial ecosystems a little bit, and global carbon cycle in some detail. And the focus is strongly on observations at various time scales. We'll also touch on paleoclimate. So the material following after this chapter will build on this, but obviously this is in the context of mitigation and adaptation and not just on climate change science. So we will have details as we go along with the emphasis on the terrestrial component. There is a lot of material now on ocean as a sink for carbon, not only natural sink, but also as a place to sequester additional carbon, which we will touch on a little bit later on from other papers and material and other books as well. Okay, so fundamentals of climate change science. We will look basically mention weather, feedbacks, climate, and climate change. I think you all have a good sense of what weather is. It's what happens on day-to-day time scale and changes sometimes even within a day. You can start sunny, have afternoon showers, evening cool breeze, and so on, depending on whether you are on the coast or interior, mountains, high latitudes, tropics, etc. And climate is basically a low frequency representation of weather. You can think of it as averaged weather. A better way may be to go back to the old way of thinking about it. So if you are thinking about, let's say this is December 25th, Christmas Day, Merry Christmas, then you can think of August 25th wherever you are, and you pretty much expect that August 25th is most likely going to be warmer than December 25th. So that's climate. You expect that August 25th will be warmer than December 25th. But because of some front or some heat wave or whatever, weather may in fact turn out to be warmer on August 25th than on December 25th than August 25th. So weather is what we get, whereas climate is what we expect. Okay, feedbacks. If you think about weather and it changes several times during the day, then that should tell you that sun is going up and down and there is a seasonal cycle. So if weather is changing within a day, there must be something happening. These are the various feedback: evaporation from the ocean, rainfall, clouds, winds coming in, jet stream moving in, etc. So there are internal feedbacks. Given the intrinsic time scales of solar forcing at daily time scale and seasonal time scale, and then we will add later on the longer time scales of orbital forcing where the obliquity, ellipticity, and precession also change on thousands of year timescales. The Earth system has internal feedbacks, ways of storing the energy in the ocean and releasing it, or storing it in glaciers and releasing it, and so on. So those feedbacks become very critical for creating this huge spectrum of timescales, which matter a lot. And climate change within that is some change over a certain time scale. It's a little bit arbitrary because we will see that there are changes happening on all sorts of time scales. But in the current context of this course, we are essentially worrying about human lifetimes. So a 100-year time scale is what we are looking at in terms of climate change, the warming, the sea level rise, rainfall distributions, glacier melts, and so on. When we talked about the introduction to the course, we mentioned that by 1700s there was already meteorology and oceanography defined in some ways. In 1800s we were already having international organizations and international ocean expeditions and so on. Koppen, I don't know how you pronounce the name, in 1918 actually looked at the vegetation distribution, and without having the rainfall data, he made these classifications which essentially correspond to rainfall distribution. So it was kind of a proxy for rainfall. So you can see the various characteristics here: tropical, dry, mild temperature, snow and polar, fully humid, monsoon, dry summer, and so on. So even now you can see that the Köppen climate classification for 1901 to 2010 from this paper shows these various classifications. So there is a huge dependence of vegetation and deserts, distribution of deserts, humid areas, dry areas, semi-arid regions, etc. on the climate, obviously. Then the question is, how are we altering the distribution of vegetation that would naturally occur, and how would that feed back to climate directly through changes in reflectivity or albedo, or indirectly through carbon cycle, for example. So we will look at those sorts of details. So compared to Köppen's time in 1918, now we have many more observations. These are what are called ECVs, or essential climate variables, defined by the global climate observation system under the World Meteorological Organization and the International Ocean Commission under the under UNESCO and UN Environment Office. So you have upper atmosphere, surface atmosphere, atmospheric composition, chemistry, etc., the cryosphere, anthroposphere, so socioeconomic and demographic and land use and other data, biosphere, hydrosphere, subsurface ocean physics, ocean biology and ecosystems, surface ocean physics, ocean biogeochemistry. So you cannot do carbon cycle without having ocean biogeochemistry as well. So this is just a snapshot of the observing systems that exist in the ocean. May 2017 is when this figure is showing. So they include various things like Argo floats, which are parked at some depth to avoid biofouling. They go up and down at a frequency like 10 days. They collect temperature and salinity data and beam it to the satellite. There are also deep Argos, which are measuring deep ocean warming, and biogeochemical Argo, which are measuring chlorophyll, oxygen, and other things. There are surface drifters, fixed platforms like these, coastal observations, open ocean observations, volunteer observing ships. So you can see some tracks there, which is not very evident in this noisy plot. But there are also a bunch of satellites that we will look at a little bit later. Okay, so that's kind of the introduction to the beginning of climate science.